Welcome back to another explainer. Today we're looking at something that honestly feels straight out of a sci-fi movie. We're going to deconstruct the MRI, magnetic resonance imaging. Think about it. We have the ability to peer clearly inside a living, breathing human body, creating these incredibly realistic, transparent 3D models, and we do the whole shebang without a single surgical incision. Oh, and no ionizing radiation either, like you'd get with an X-ray or CT scan. Instead, we're talking about a system using immense magnetic forces, radio waves, and just serious computing power to render photorealistic imagery of our internal anatomy. So, let's break down exactly how this modern medical superpower actually works.
Okay, let's dive right in. The crucial anchor for this entire technology is actually surprisingly simple. You and I are about 60% water. Now, why does that matter for an MRI? Well, water molecules are made of oxygen and hydrogen, right? And it's those hydrogen atoms that are the absolute stars of the show here, because every single hydrogen atom has a single proton in its nucleus. And since these protons spin, they basically act like millions of tiny, glowing compass needles inside of you. Normally, these biological magnets are just pointing in totally random directions, complete chaos. So, to get a clear image, we have to bring some order to that chaos.
And to command all those tiny compass needles, you need immense power. When a patient enters an MRI scanner, they're engulfed by an incredibly powerful magnetic field, typically rated at 1.5 to 3 Tesla. Just to put that into perspective, this magnetic force field is so intensely strong that it physically forces those random hydrogen protons to just snap to attention. Most of them align either parallel or anti-parallel to the magnetic field itself. Ultimately, you get a slight excess of protons aligning parallel, and that creates a measurable net magnetization. Basically, it's the blank canvas the MRI needs to start painting a picture.
So we can actually break this incredible transformation down into 5 core phases: entering the scanner, the radio frequency pulse, relaxation, signal detection, and finally, image formation. Let's look at exactly what happens the very second those protons snap into alignment.
All right, with the protons perfectly aligned, the machine kicks off the next phase. It sends out a carefully tuned radio frequency pulse designed to interact specifically with hydrogen. You can think of this pulse as a quick burst of energy that physically tips those aligned protons away from the main magnetic field. It knocks them right out of equilibrium. But here's the catch. That pulse is only temporary. As soon as it stops, those protons naturally just want to go back home. They immediately start returning to their original magnetized alignment.
And as those protons return to equilibrium, they undergo a process we call relaxation. Now here is where the absolute magic happens. They don't all relax in the exact same way. We actually have 2 very important processes happening at the exact same time: T1 longitudinal recovery and T2 transverse decay. The sheer genius of the MRI is that protons in different types of human tissues recover at totally different rates. And it's precisely those varying rates of relaxation that create the incredible, high-contrast images in the final scan. So, as those protons find their way back home to equilibrium, they release the energy they just absorbed from that radio frequency pulse. And they release it as these incredibly tiny radio signals. I like to think of them as extremely weak echoes of hydrogen. Because these signals are so faint, the MRI uses highly sensitive receiver coils placed right around the specific body part being scanned to catch them. It then relies on some seriously advanced electronics to amplify those weak biological echoes into something a computer can actually read.
But wait, how does the machine actually know exactly where in your body a specific echo came from? Well, that's where gradient coils come in. These coils slightly, and I mean very slightly, change the magnetic field across different parts of your body. Because the field varies, the signals vary, depending on their exact location. Then, the computer deploys this advanced mathematical technique called a Fourier transform. This math decodes all those varying signals, pinpointing their exact origin coordinates. This is the literal moment the raw data transforms into those gorgeous photorealistic cross-sectional slices on the doctor's screen.
Now, because MRI fundamentally relies on hydrogen, which is mostly found in water and fat, different tissues behave totally differently. Fat, for instance, produces very strong, bright signals on a lot of MRI sequences. But what about bone? Well, bone actually contains very little hydrogen. So on an MRI, bone appears completely dark. In air, like in your lungs, it produces almost zero signal at all. Water behaves a bit differently depending on the exact imaging sequence used, which actually brings us to how doctors customize these scans.
You can kind of think of radiologists as highly specialized photographers. They select from this precise menu of pulse sequences to highlight very specific tissue characteristics. We're talking T1 and T2 weighted scans, flare, steered diffusion weighted imaging or DWI. There's also gradient echo, which is GRE, and susceptibility weighted imaging, SWI. Honestly, each one of these sequences tells a slightly different story just by tweaking how the radio waves and the magnetic field interact with the body's water and fat. Of course, powering a futuristic diagnostic tool like this requires some truly astonishing hardware. Right at the core is the massive superconducting magnet. Tucked inside of that, you've got the gradient coils adjusting the field, plus the RF transmitters and receiver coils handling that radio frequency dance we just talked about. But to keep that superconducting magnet working properly, it requires a heavy-duty cryogenic cooling system. This system actually runs on liquid helium to keep things unbelievably cold. And finally, the whole setup is rooted to a high-powered computer workstation to crunch those Fourier transforms.
But what makes all of this crazy engineering so worthwhile is the clinical application. Without using a single drop of harmful ionizing radiation, MRIs are deployed for intricate brain and spine imaging, crucial sports medicine diagnostics, and even cancer detection. They're used for assessing liver and heart health, visualizing really complex blood vessels, and examining pelvic organs. It is just a wildly fast, non-invasive way to detect strokes, locate tumors, and assess severe internal injuries with stunning clarity.
Now, with all that power comes a very real need for strict safety protocols. Because remember, that powerful 1.5 to 3 Tesla magnetic field, it is always on. It literally never turns off. That means the invisible pull of the magnet can dangerously attract metallic objects in the room. This is exactly why patients with certain metallic implants have to be carefully evaluated before they even get close to an MRI room. Also, because those gradient coils we mentioned are constantly shifting the magnetic field, they produce these incredibly loud knocking sounds. So ear protection for the patient is an absolute, non-negotiable requirement during a scan.
This technology is already awe-inspiring, but it definitely isn't standing still. Today, modern MRI systems are integrating artificial intelligence to drastically reduce scan times and continuously improve image quality. These new advancements are pushing the absolute boundaries of speed, resolution, and diagnostic accuracy. MRI remains, without a doubt, one of the safest and most powerful imaging tools in modern medicine, so it leaves us with a pretty fascinating question to ponder. As AI steps in to continuously refine this incredible medical superpower, what new frontiers of the human body, what hidden truths will MRIs reveal next? Thanks for joining me on this explainer, and I hope you're walking away with a much clearer picture of the science happening behind the scan.